Hi everyone and welcome to a new discussion. Today I'm talking to David Trillo Fernandez regarding quantum advantages for transportation tasks, projectiles, rockets, and quantum backflow. What we're going to be focused on is transporting particles from one point to another and the kinds of advantages that a quantum mechanical formulation can offer compared to the classical one. I hope you enjoy the discussion. We have now on the screen this paper that you wrote called Quantum Advantages for Transportation Tasks, Projectiles, Rockets, and Quantum Backflow. In general, we're going to be talking about transportation of quantum particles or quantum systems. Would you mind describing, as a starting point for this, what quantum projectiles are? I guess that would be the best one of these terms to start with.
Yeah, okay, well, maybe it's not the best name. With quantum projectile, we just mean like it's just a particle. Okay, like a normal projectile is also a particle that you would think in classical mechanics as a particle. But here we think about it in quantum mechanics, just one particle. And we call it a projectile because we are interested in a specific task, which is to get it somewhere far away. Okay, so it's just, somehow it's just mnemotechnia to remember what we're interested in, no? But it's just a particle and we're interested in it going very far. Just like a projectile in classical mechanics is a particle that we send somewhere, no?
Right.
Maybe it's not. It doesn't necessarily have a relation to like weapons or ballistics and stuff. No, it's just to remind ourselves, this is what we want to do with this particle.
Yes. If we think about the context at which we're investigating this, so as you mentioned before, it's a transportation task, and particularly we're interested in when these particles would move faster or slower than classical particles. Could you maybe give some background as to why there would be like even an investigation conducted on that? Like, what's the rationale for why there might be a case where quantum particles are moving faster from one place to another than a classical particle? Like, do you have some intuition for that?
Well, I mean, when we started this project, we really had no idea if this was possible or not. No, like we started with this question: is this possible? Like, there are lots of things in quantum mechanics that are very bizarre, very unintuitive, and we thought, has anyone looked at this problem? And we saw that not really. I was like, maybe there's something, maybe there's not, we don't know. We tried it, and it turns out that you can do it faster than classical mechanics, no? That's why we made a paper about it. But like many things in science, you try many things, no? And most ideas don't work. This one just did. So, but we really didn't know before doing this. So it actually came as a surprise for us as well.
And there was no indication leading up to it either that sort of, made you suspicious that maybe this is something that would happen?
Well, yes. Once we set up the mathematical problem and started studying it, we were like, "Wait, this could happen." No, like at each step of all the computations that we did, there was nothing that would immediately say, it cannot happen because of this very easy reason. It's like, no, it could still happen. There's nothing preventing it from happening. And then it became a question of how big is the effect, no?
Right.
At the end. But yeah, we spent quite a bit of time proving that there is an effect. This is of course not trivial to begin with, but yeah, maybe there is one intuition that I could give you about this, and it's about tunneling. I don't know if you're familiar with tunneling.
Yep.
You have a quantum particle. Okay, but maybe I'll explain it anyways for your viewers.
Yeah, please do.
You have a quantum particle in some potential. Well, you can think of it trapped in a box, no? And there is some probability of this particle escaping the box. Unless the box has infinite energy or whatever. There is some probability in the real world of the particle escaping the box. And this is a bit the same, only that there's not a box. You have a particle, there's no box, but there's still some probability of the particle suddenly being very far away. So the intuition is that it's tunneling without a mountain to tunnel through. So this was my intuition, at least at the beginning. Maybe this could happen because of this. But who knows? No, in the end you have to do the calculation to see that it actually happens. But yeah, so tunneling without a tunnel really, because nothing preventing the particle from moving.
Right. I want to make a small diversion from the chronological order. Let's say that we would go through the paper and just raise the topic of sort of the results quite early now, just because of the tunneling that we started talking about. So in the investigations that you did, you found that the let's say quantum advantage that you get from these particles in transition are independent of the distance that you're considering. Yeah. And is the reason why that is so surprising, just to get back to the tunneling example that you did now, that tunneling is one thing that decays, I think exponentially with the amount of distance that you would need to tunnel? Is that the rationale for sort of why you would expect Yes. Is that the reason why you would expect also in a situation like this that maybe you have some effect, but that it would be very localized, let's say, that you would have like pretty much the same effect for a small distance as a long one?
Yeah, essentially. I mean, but it also comes, so that's one thing, but there's also the usual classical intuition, no? That the farther you want to go, the more time you need, no? The more difficult it is. Doesn't seem to hold in this case for this particular effect. And it has to do with the way like we compare the quantum and the classical results and some other things. But yeah, it was very unintuitive. I remember I spent a lot of time thinking why this is happening. Our classical intuition, even though I'm a quantum physicist, still I have a classical intuition. It's
Right.
like, why is this happening? But yeah, but the fact that also tunneling is exponentially small, of course, because there's no barrier, there's no point at which the exponentially small vanishing starts, no? That's the reason. It cannot start at any point because there's no barrier anywhere. And this happens at the barrier and then from it onwards. So yeah, it's quite curious, yeah.
So maybe if we look at what I'm sharing on the screen now, which is the experimental setup for this, to get back onto the chronological order of things, would you mind describing just how you set up the experiment to actually evaluate whether there would be some advantage for these quantum systems or these quantum particles?
Okay, so well, this is not an experimental setup. This is a very sketchy diagram. I mean, you could not go to an experimentalist with this drawing. I was like, please do. No, of course not. I mean, this is just a picture to like set up notation and what we're doing. No, for example, I also draw there like a cannon throwing a particle, but there's no gravity in this experiment. There's no cannon that throws a particle. It's just a pretty drawing for the paper. The way you set up the experiment, well, it's quite one possible way not to set up an experiment is to prepare a particle confined in a certain region, the thing that I showed there from 0 to L. You can trap particles like very precisely with like atomic tweezers and things like with lasers and stuff like that. And then at some point, prepare it in the very particular state that we need, and then remove the barrier and let it evolve freely. And then measure the position where you're interested in the position. So that's how you would set up an experiment like this. And of course, there's lots of problems with experimental setups that we do not consider here. Like, for example, removing this barrier imposes some disturbance on the particle itself. It's complicated. But the setup would be like that. Prepare somehow a particle confined in a region in the particular state that we need, and then let it evolve.
Okay, and there are three particular investigations that you're doing with this kind of setup. I won't call it experimental setup, but nevertheless, like the drawing. So you have the standard problem, you have the extended standard problem, and then you have the constrained projectile scenario. Would you mind just describing, before we go into the details of these and what the findings were for each, what they represent?
Well, the standard problem is what we've been talking about all the time. It's exactly that. For the extended standard problem, well, one way to see it is that you give the classical particle some advantage, like I let it go before, and we compare. And what was the other one you mentioned? The constrained one.
Projectile.
Yeah. So that one, and unless I got the names mixed up, which sometimes happens in my head, the constrained one is where you not only constrain. Of course, because I didn't. This is important. Yeah, for the standard problem. So we're comparing the quantum particle with a classical particle with the same momentum, let's say. Okay, so this is important because I can always give the classical particle more energy and it goes faster to the right. So to make this a fair comparison, we say, okay, the classical particle has the same momentum as the quantum particle. Okay, and in the constrained one, we say not only has the same momentum, it also starts at the same position. Let's say, okay, it's about probability distributions, but the idea is that we don't constrain only the momentum, but also the position. Because for a classical particle, I mean, if you want to send a particle very far to the right, and it starts constrained in some region, the optimal strategy is to put it at the rightmost part of that region. Okay, but here we're like, no, okay, what if we also constrain it to be at the same position as the quantum one? Okay, I mean, this is just mathematical variations on the problem to see what we can do. But really the important one is the original one. Is
the momentum.
Yeah, constraining the momentum to be the same, because it's the one that has more meaning, really. Because what does it mean to constrain the position to be the same? It's a very artificial problem. It was just to see if we could go beyond what we do, and we can, but I don't see much physical interpretation for that, honestly.
Okay, so we're talking about two concepts in the paper then, and we have ultra-fast and ultra-slow projectiles. Just to quantify a little bit what we mean when we talk about the quantum advantage for those, would you mind describing first of all what they are, and then also after you define that, just how do we quantify how much faster one is or how much slower one is?
Yeah, okay, so, well, the ultra-fast and ultra-slow, we just mean, we are comparing these quantum and classical particles, or projectiles, let's call it, and, okay, at the beginning we didn't know if there was this effect where the quantum particle arrives before or after, no?
Yeah.
And we say that if the probability of finding the quantum particle in that region we're interested on, and after that the amount of time that we're waiting is bigger than the probability of finding the classical particle there, then we call that an ultra-fast quantum projectile. Just to say, okay, this is one of those which has this advantage.
Right.
And then we also noticed that there exist quantum particles which arrive there with a lower probability of success, or if you want to think about it, slower than it's possible for a classical particle to go there. And we call this ultra-slow. This is just, again, an abbreviation for this effect. No? Ultra-fast means with this state we get there faster, let's say. And what do I mean by faster? What figure of merit are we comparing? No? This is very important. This is crucial for what we're talking about. So there's a big problem in quantum physics because you cannot define. You cannot really define what time is. Time in the Schrödinger equation and in these other many things is just this parameter that grows continuously. No, but if you want to measure how long does it take for something to happen, or at which time does the particle arrive at this point, these are complicated things because in quantum mechanics observables are modeled with operators, and it's impossible to define a time operator that works well with the Hamiltonian and everything. I mean, the problems are very subtle, but they are there. So in particular, it's quite difficult, if not impossible, to define an arrival time operator, to say, I measure at which time a particle arrives here, and this is the measurement that I do. You really have, I mean, there's lots and lots of papers about this, and really you have to get into like the particular experimental design that you have, but in this abstract way, we can just say it's impossible. Okay, it's very difficult. So we didn't want to get into that discussion because it's really complicated, and we take what is called more of an operational point of view, which is, okay, I just want to know if the particle is here or not, and instead of measuring at which time it gets there, I wait a certain amount of time, and then I look and I see if it's there or not after some time. No, and if I see it's there, okay, I make a note, it's there. I repeat the experiment many times, and in the end I get a probability distribution. No, 50 times it was there and 35 it was not there. So what's the probability? And then you do some statistical analysis and you get a probability of the particle being there in this experiment after a certain amount of time. And then you can do the computation, what would be the probability of a classical particle with the same momentum probability distribution, and you get some number. And then you compare these two probabilities of succeeding in your experiment. And if the quantum one is bigger, then this is the ultrafast projectile. No? And this is the figure of merit we're comparing. It's the probability of observing the particle in this region that I draw here from A onwards, of the quantum projectile versus the classical projectile. Okay, if you want to think about it as real projectiles, is you shoot the quantum particle, and the people who are, well, the target that's there is a dummy target, no? Because we don't want to shoot at anyone. The dummy target is there, acts as a measurement. If the particle arrives there, the dummy target will see it, no? And what's the probability that the dummy target will see this particle after this amount of time? It's 3/4. And what's the classical one? 1/2, let's say. So 3/4 is bigger than 1/2. So it's more likely that the quantum particle arrives there after such amount of time. Okay, and this procedure of looking at only like a very well-defined measurement and just looking at those probabilities is what's called this operational point of view. No, like I don't care about the modeling details. What is this time arrival operator? It's model dependent. It's very complicated. Forget about that. Just look at the probabilities. Well, however you model this, I don't care. The probabilities will speak for themselves. This is called the operational approach to quantum mechanics, and it's very useful for these things.
Okay, maybe this is a naive follow-up question, but for the classical scenario, do you also receive a probability distribution for this? Like what is the probabilistic part of the
Yeah.
classical approach?
So this is maybe you have to think about it. I don't know if you are familiar with any statistical physics.
Yes,
Well,
somewhat. I
never
mean,
mind, never mind. So I say I want the classical particle to have the same momentum as the quantum particle. Okay, but the momentum of a quantum particle is not well defined. There's not a number that you can say, it has momentum 3 units of momentum. Because if it were, the particle would be evenly spread in space. And this is
right.
completely unphysical. So in reality, what you have in quantum mechanics is you have a probability amplitude of the momentum being a particular value. And when you take the modulus of this squared, this turns into a probability distribution of when you measure the momentum having that value. Okay, and this probability distribution, we say, is the probability distribution of the momentum of the classical particle. You have to imagine an ensemble of particles, of classical particles, that have a probability distribution of the momentum. Like if it's a Gaussian, for example, there's like a Gaussian distribution of momentum for each particle. It has a momentum with a certain probability. Okay, this is very common. When you prepare particles from an oven, for example, you heat particles in an oven so that they get speed. Well, this was done a long time ago. I'm not sure if they do this anymore. But the particles will come out with a random momentum, even though they're classical. Okay, so what is this probability distribution of the momentum? This is what we
so you're still taking into
the
account the
probability
uncertainty.
distribution of the momentum is the same.
Right. You're still taking into account the uncertainty principle when it comes to the classical particles that you're introducing.
Well, it's not for the classical particles. It's not the uncertainty principle. This is to motivate why we need a probability distribution in the quantum case. Okay, but then the classical, we say, okay, we are assuming that we also don't. Maybe you can think of, you don't know the momentum of the classical particle. No, with something, it has some probability distribution. You get particles given to you with some probability distribution of momentum.
Okay.
Like when you shoot a bullet out of a gun, it doesn't have exactly the same momentum every time. No,
Okay.
It will come
Okay.
with
So all the uncertainty.
it will be very centered on a particular value, but it will be it will have small deviations of that. No, that's a probability distribution of a momentum.
Yeah. Okay, so that gets to the heart of my question. The uncertainty in the probability distribution for the classical particle is solely derived from the fact that the momentum that we give it to begin with is a distribution itself. We have no other in-source, there's no other in-source of randomness, let's say, in the process that we consider for the classical particle.
No, not necessarily. Of course, you can think of probability distributions in two ways. No, one that is that it comes out with a probability distribution, and another one which is I don't know the momentum, but it follows this probability distribution. My knowledge follows some probability distribution.
Right.
So you can think about it both ways. The computation is the same. So in both those scenarios, this will hold.
Okay, very good. The next thing I want to clarify is when we quantify this now. So we say here the maximum quantum advantage, blah, blah, blah. When we say maximum quantum advantage in this setting, because we will come back to that term, what are we exactly referring to? Are we referring to the factor that differentiates these probability distributions in the arrival? Or what is it exactly that we're quantifying when we say maximum quantum advantage?
Yes, so it's the difference of the probability distribution. So it's not the division, it's a difference. So I take the quantum probability distribution and I subtract the classical one. How much bigger is it additively? No? And this I compare with all possible quantum states. So each quantum state will give me a probability distribution at the end. I take the biggest of all of these, all of these differences. Which is to say, what is the maximum advantage I can get using quantum mechanics? No, because
Okay, good. So then let's start focusing on the actual experiment. If we begin with the first one, the unconstrained problem, what were your findings when it comes to the propagation times here? Maybe if we start there.
Okay, let me again clarify. This is not an experiment. This is
yes.
Sorry, but I want this to make very clear. No experiment has been done on this. And now, can you repeat the question again?
Would you mind summarizing what the findings were from your investigation when it comes to the unconstrained problem?
Yes, okay. Well, I mean, you can see it there in the figure 1 is that the maximum quantum advantage is bounded by this very small number. So like 0.04. Well, no, actually, that's the conjecture value for this. The upper bound that we gave was 0.0725, whatever. Okay, so we see that this advantage we see several things. One, it exists, so it is possible to go faster in the sense of it's more likely to get there in a certain amount of time. And second, it's not very big, the improvement. So that's just two main things. Yeah.
What is this constant, if we start talking about this one? Could you give some background as to where that comes from?
So that comes from a different quantum effect that was discussed, found a long time ago, called the quantum backflow, which also appears in the title of the paper. So quantum backflow is this phenomenon in which you have a particle, a quantum particle, okay? It has some certain distribution of momentum, and I say this distribution only has support in the positive real axis, which is to say, if I measure the momentum of this particle, it will always come to be positive, okay? Positive means moving to the right.
Right.
So that means this quantum particle only has momentum which should make it move to the right. Still, you can find that it moves to the left. Okay, this is a really cool quantum effect that very few people know of because it's not it's not as popular as tunneling, even though it's very similar in some sort. And the Bracken-Melloy constant that I write here about is what is the maximum amount of moving to the left that you can see in such a situation. Okay, and then it's in a dimensional unit, it doesn't matter. The biggest one, everything moving to the left, would be like 1. Okay, 1 is a trivial one. And it's conjectured to be like 0.04. Doesn't matter what this means, it means that it moves to the left, but very little. It can only move very little before it starts moving to the right again. Okay, but this is possible, and it turns out that this number is exactly the same as the maximal quantum advantage of this projectile scenario. This was, amazing.
If we talk about the figure here when we're on when we're on this topic, because I think this figure illustrates quite well how you also converge onto this value. So you have a figure that I'll let you explain in just a bit, but that has alpha here that I would like you to explain, like what that constant means or what that variable means, and then phi of alpha here, which is the quantum advantage of that particular scenario. Could you please just describe what this one means, and I think that will set some additional context.
Okay, so maybe if you go first a bit to figure 1 again.
Yeah.
So as you can see, there are several parameters in this theoretical research. So there's the what I call L, which is the size of the region on which the particle is confined at first. Then there's this A, which is the distance to the target region. Then there's this delta T, which is the time that we wait until we measure position. And then, of course, there's the mass of the particle, which I don't draw there. Okay, so we see that the quantum advantage that we get, of course, in principle, should depend on all these parameters, right? But it turns out that it only depends on a combination of them, which is alpha. Now you can go to the figure 2. I don't write what alpha is there.
Alpha is ml squared over delta T.
Yeah, alpha is m. So this is some combination of parameters: the mass, the size of the confined region squared, divided by the time that you wait. As you can see, the distance to the target region plays no role. That's what I mean. But only on this quotient, on this ratio of parameters, is what the quantum advantage depends on. And so here we plot, since it only depends on one parameter, we can plot it in a 2D thing. And we plot alpha here, and phi of alpha is again the quantum advantage that you get, no? And this blue curve is the advantage. When alpha is finite, we can actually compute this to a very good precision. Well, until alpha is 100 or so, then the computer stops working. And yeah, in the black dot, we see the conjectured value when alpha goes to infinity. When alpha is infinity, so when you have an infinitely large confining region, which is really what you want, no? Because you don't want. It's easier to have a confining region that's infinitely large than one that is short. But yeah, so that's it. I mean, you can see, okay, you say that this shows a convergence, but I don't see any convergence here. If it's very small. And actually, there's a group right now in the University of York, I think, that is very carefully looking at this convergence, and they're trying to get more precise values, and they're doing amazing work on this. But it turns, if they are right, it's still unpublished, no? But if they are right, this convergence is really, really slow. So you really need to go to very high alphas to get close to the conjecture value. I mean, we don't even know if this value is right. Maybe it's 0.07.
Yeah. Okay. How come that parameter value has not been specified to a larger degree? I forgot what the constant was called now, but I'm talking about the CBM constant. It's still conjecture what the value of that is, and what is the background regarding measuring that? So, like, do you know some of the background as to why that is not very well specified yet at this point?
Yeah, I mean, the reason is because it's very difficult. It's a very difficult problem. So people have tried, but they didn't manage. No, I mean, it doesn't matter.
Yeah.
To approach this value from below is easier because you need to find examples. No, find an example of state that gets close to this value. And this they have done a lot. Well, I mean, we don't know because we don't know the actual value. But imagining that is this, yeah, they've gotten quite close.
Yeah.
And the problem is that it's also very difficult experimentally to do this, because you need to prepare these very particular states, which are very complicated and require a lot of control on your quantum system. It's also a quantum system on position, which is way more complicated than the things that you see in a quantum computer, which is just really a two-level system, atoms or superconducting qubits or whatever. Controlling the position of a quantum system is complicated, and you have to control the position to prepare the initial state so that then it evolves correctly. It's very difficult. There's been some experiments with classical light trying to do this, but yeah, it's a classical experiment simulating what would happen if the quantum thing worked. No? So it's not quite the same. There's quite a lot of work from the quantum backflow community on trying to make this more experimentally friendly. But yeah, we could still call this an open problem because no experimentalist has yet achieved this level of control on a system to be able to perform these experiments. It's quite complicated. No? And why don't we know the constant with more accuracy? It's a terribly complicated equation that you have to solve. It's an eigenvalue problem of a really complicated operator. We don't know if the spectrum is discrete or not. Lots of hard functional analysis that still needs to be solved.
Do you have some intuition as to why this constant might be the bound for this kind of problem? Like if we're talking about the quantum advantage again, and why, from a conceptual point of view, this constant reappears in this problem?
Yeah.
Also with a factor 1, let's say, in between. Like it seems to be agnostic in some sense to... it's almost like you would allow for one sort of backflow throughout this propagation, irrespective of how long the propagation is. Like maybe I'm thinking about that from a very naive perspective, but nevertheless, like, is there some intuition to tie these two together that is at least speculatively interesting? Like that we can say something about why this constant might appear in this kind of scenario.
Yeah, that's a very interesting question which occupied me for quite a while, but there is a way. So this may sound a bit weird, but we can rotate the backflow problem to become this problem. Never mind what this means. So you see this problem in what's called phase space. You think of position and momentum on equal footing, and then you see what this problem means in phase space, and somehow you can transform one problem into another using some phase space transformation. I mean, it's really a mathematical intuition. It's hard to express without mathematics, but...
Well, I guess you have the similar circumstance. I guess you have a similar circumstance if you compare the ultra-slow propagation, right? Like, that pretty much is the backflow problem, if you will.
Yes. Yeah, it's a similar thing. You should think about the role of momentum in the backflow problem is played by position in our problem, and the role of position in their problem is played by momentum in our problem. It's slightly more complicated than that, but that's the idea. Somehow position and momentum you just change position and momentum somehow. Transformation is a bit more complicated than changing them, and one problem becomes the other. And then naturally, all that you know about one problem can be translated to things you know about the other. This is why, using our techniques for this problem, we can bound this constant for their problem in some sort of novel way, no? So they're intimately related mathematically. I don't know if I can give you an intuition better than this. This is really what I have.
Okay, no, understood. If we move on to the next figure, because then you also have a representation, I think, of the quantum advantage. If we talk about part A about this figure, First of all, what I would like you to clarify is just we have a Wigner function here. Apologies if I'm butchering that name. Would you mind just explaining what that is and how that's useful in the circumstance?
Yeah, well, so I just said maybe looking at this problem in phase space is really useful because of all these relations to other problems. Okay, and this Wigner function is really the way you represent quantum states in phase space. So there's a lot of, actually there's a myriad formulations of quantum mechanics. The one that you probably know is with the Schrödinger equation, no, and the wave function and things.
Right.
There's also one using operator algebras, which I like a lot, but it never caught on really. And then there's this one is another possibility. Usually representing, instead of a wave function, which is like a function of position, no? The wave function usually in the Schrödinger picture is the probability amplitude of detecting a particle at a certain position.
Right.
Whatever this means. The Wigner function is not a probability amplitude, it's a pseudo probability distribution, no matter what this means. It's something which tells you the probability, let me put probability in quotation marks, the probability of finding a particle with a certain position and a certain momentum at the same time. Okay, so you're not just looking at position, you're looking at position and momentum. There's a problem with this, and is that you cannot measure position and momentum at the same time. This is the Heisenberg uncertainty principle. And how do you solve this problem? How do you get then a probability distribution that tells you, this is the probability of having this position with this momentum? Well, the probability becomes negative sometimes. This is why I put probability in quotation mark. It's not a probability distribution. It's something that somehow works, but sometimes it gives you negative probabilities when the uncertainty principle comes into effect. What does this mean physically? Not much. It means that you cannot, it means a lot. It means that you can really not assign a probability to measuring a position or momentum at the same time, but rather you take a small area around that position and momentum, and then you integrate this function, and that then is a probability of finding the particle on this, with this position and momentum, not in some area, like position maybe between 3 and 3 and momentum between 3 and 3, minus 3 and 3. Okay, so this is an area, and when you integrate Wigner functions over big enough areas, bigger to counteract the uncertainty principle, then you get a probability. Okay, so there is a way to do this, and you can do all quantum mechanics like this. It's usually very complicated, like there's lots of open questions about Wigner functions, what properties they have. Like we don't even know what's the set of all Wigner functions. Like we know the set of all wave functions is the square integral functions on the line, no? But what's the set of all Wigner functions? No idea, no one knows. Lots of papers about this. Anyway, it's very useful for a particular problem because we really looking in phase space is enough. And I mean, you can work numerically with Wigner functions, no? And this is what we do here. We numerically represent some Wigner functions which are obtained of some particle which would obtain a big advantage. So this here, for example, the part A of the figure. It's the state you should prepare a particle, well, the state in phase space, no? So I'm giving you from the Wigner function you can recover the wave function, and vice versa. So I give you a Wigner function and I leave to you to figure out what the wave function is. This is very difficult. But anyway, you can try. I mean, numerically you can approximate it.
Okay.
And so we give you the Wigner function because it's easier for us to compute. And you can see, for example, that it has some negative values, some there around 0. So this is important. You really need negativity of the Wigner function, otherwise you have classical things. But yeah, so this is what we do. So instead of giving you a wave function, we give you a Wigner function because it's more convenient for us. And this is one formulation of quantum mechanics which is also not much used because it's a limited value many times, but there's a lot of concrete problems in which suddenly it becomes crucial, and this is one of them.
Okay, so I take it then that all the negative regions of this function would be limited in area. Like in this space, they'll be limited in area such that if the, well, whatever area you consider that's large enough, that would integrate to something positive.
So the area you need to consider is so that the uncertainty principle would be satisfied, so that you can measure a position and momentum between those values. Because the uncertainty principle is satisfied. Okay. So the area is very small. It has to do with the Planck constant.
And from
But
this
of
figure,
course,
what can we really say from this? So we have some high amplitude here, which I presume corresponds to a high likelihood of finding the position or finding the particle in this particular
yes. Yes.
state. Nevertheless, what does that tell us about the problem itself?
Okay, so first about what the high amplitude means. If you want,
Mhm.
you can integrate on lines the Wigner function. If you integrate so you integrate the momentum, you recover the wave function. So you recover the amplitude distribution of position if you integrate the momentum. Okay, so you have to think of lines integrating this function over lines to see what this probability of position. But yeah, you see that at 0, it's always positive, no, and it's where it's the highest. This, for example, means that the optimal strategy for the quantum particle is to have really a lot of probability of being at the rightmost part of the confining region, which is intuitive. It's what the classical particle wants to do. It wants to start as close as possible to the target region. Well, the quantum particle as well, right? It's just that there's a negative probability of finding it immediately to the left, but whatever. Of course, this is nonsense. No, it's just averaging whatever. But yeah, this is what it means. Another thing that we see is that it has lots of waviness. A lot of waviness. This means that it's very complicated to prepare this in a laboratory. That's what that means. Let's just say that means that.
Okay, so the smoother in general this would be, the easier it is to experimentally get the conditions right, or?
Yeah, I mean, depends, no? But in this case, yes.
Okay. Okay, good. So with this problem explained, I don't know if there's anything you would like to add, like on the initial unconstrained problem before we start talking about, for example, the quantum rockets.
Go ahead.
Okay, so maybe let's transition to those now, and let me pull up the beautiful image that you have in the paper here as well. Could you explain the intuition behind one of these quantum rockets?
So the idea is the following. We have this advantage for the projectile, but it's very small. And we're like, well, can we make it bigger if we chain projectiles? No, I somehow shoot a quantum projectile that again shoots another projectile, and then it shoots another projectile. And this is how a rocket works. That's why we call it a quantum rocket. No, it's something that you shoot, and then it shoots something down, no, so that it gets momentum forwards. That's what burning fuel does. You're essentially shooting particles in the other direction. So we thought, okay, can we do this quantumly as well? Do we get a bigger advantage? That's why we do. Okay, it turns out that modeling a rocket in quantum mechanics is very complicated. So we consider one possibility, no, which is what we call an open combustion chamber, in which the particles can exit not only through I'm talking about up and down. This is what you're usually interested in a normal rocket, but here we're looking in one dimension, so left and right. So the particles that you shoot away from you to gain more momentum can go to the left or to the right. We don't put a constraint. Why don't we do this? Well, because to put a constraint, we would need a wall with infinite energy because of the tunneling effect. And this is very unphysical. We didn't want to do this. Let's study the simplest thing that we can think of. This is always what you should do first as well in science. So we just have it open both sides. That's what we call an open combustion chamber. In real rocket science, it would be a terrible idea. Like you don't want your fuel shooting down and up. Ridiculous. But I don't know. Maybe it works. It doesn't work. That's what we conclude from this. And we wrote it, in case someone thinks of it, don't think of it. It doesn't work. Really, the projectile is the best you can do. With this model, maybe if you close the combustion chamber, who knows? It's just modeling that is complicated. I don't know. But yeah, in this model, it doesn't work. That's what this section is about. So you get an advantage, but it's the same as if you have just thrown one particle. So what's the point really of doing this complicated thing?
So can you think about these kind of particles as some form of decay? Like if you think about radioactive decay, for example, that's something that to me looks quite similar to the intuition I got from your explanation of these kind of systems. Like you have something, you have a spontaneous emission, let's say, of a particle that escapes it. Now we have an open combustion chamber, so we allow it to go either to the left or to the right. We don't really care about it. My follow-up question as a consequence to this would be, if you have something like me trying to think about this intuitively, if you have a system like that could emit particles in either direction with some form of emission frequency, you would expect perhaps the distribution, like even though the average of the distribution would remain the same, maybe it would be more skewed, or maybe not skewed, but like the variance of the distribution would increase. Is that something you were able to observe in any way, or is it like the distribution that you got from, as far as you were able to tell, really identical to the one that you got in the single projectile case?
So, okay, so there were two parts to this question. So the first one, yes, of course, you can think about it as decay, no? It's the same thing, really. It's just that we model it with a bit more of quantum information, with quantum information mines, with these CPTP channels and stuff. But yeah, it's decay, no? It's one particle shooting another particle from nowhere. And then, but you shouldn't think about it as the particle going to the left or to the right, no? It somehow is a particle that splits in two, and now, well, we have the particle that we're interested in, and then the other one, which we call the fuel, has a probability distribution in position, which can have parts to the left and also to the right. Okay, so it's not.
But you're still modeling. You're still just modeling
to the right. Both of them at the same time.
But you're still just modeling the like. So after a split, let's say you're still just modeling one of these, like let's say the bigger one or the one in focus, like the other one that splits out from it. If we consider these now as two independent particles, you don't model the arrival time, let's say, of the other one, right?
Yeah. We don't care about that one at all, because we're interested in the one that we do. So the other one can do whatever. We're just interested in can it propel our particle further. No, so and we're trying to find out what's the best thing that this split could do for us.
Right.
And so whatever this is, in the best case, the thing that would be the most beneficial for the other particle is not enough. That's what we're saying. And we don't care about the details of this particle. We just care about the best case scenario. Okay, and if the best case scenario doesn't work, then no scenario can work. That's the idea. So we just look at the best case scenario, whatever that is. We don't even. I don't think we even need to know what it is, but nevertheless, we look at the best case scenario, and that doesn't work. So we forget about this. And we don't pay much attention.
Okay, cool. So given what we've said now, let's focus maybe on where this brings us. Like next steps in terms of research like this, potential applications of the finding that we have. Potential areas that you would like to take similar research in the future. Do you have anything like that that's arisen that you would like to investigate more? I mean, you mentioned this particular research group earlier in the talk. Maybe you could shed some more light on that, but also on a personal level, if there is anything as a consequence of this that you're trying to follow up on going forward.
Yeah, so there's several things we would like to follow up on. I'm not sure if any of them are doable, but so first I would really like to know the value of this constant. I don't know how precise it can be. Maybe it's some sort of transcendental number that we will never figure out. But maybe it's some combination of constants. No, that makes sense. But I really want to understand this. It's a very cool mathematical problem as well. Like we have an operator. What's the spectrum of this operator? Why has no one thought about this before? It's very weird. But yeah, that's maybe a bit mathematical, no? Then I mean. Somehow we would like to model this in a more realistic scenario. This is just pure quantum mechanics, no relativity whatsoever. What happens if you do this in quantum field theory, for example? Can you do this in quantum field theory? Do you still get an advantage, or does it get washed away by the fact that you have to follow the principle of relativity? This is very complicated because it turns out, well, maybe this is a bit controversial, but we don't understand quantum field theory. At least not me. But I think no one really understands. I mean, people understand it much better than me. No, this group in York has, the leader Chris Fuster is an expert in quantum field theory. What can we measure in quantum field? How do we measure position in quantum field theory? It's a very complicated question. So somehow we got stuck into a boulder. It's like we need to advance quantum field theory somehow to continue doing this. So that's also quite interesting, though, even though it's so hard. And then I would like to see if this happens in other situations, like quantum backflow people have shown quantum backflow for like in a ring, like if you put a constant force, if you do very weird stuff, still this phenomenon persists. Somehow it's like ubiquitous in quantum mechanics. Like no matter what you're trying to do with the particle to hinder it, still a bit of backflow. Or if you try to increase it, yeah, it increases. It's quite interesting. Can we do? But here the phase space picture breaks down a bit when they do all these changes on backflow. Do we still have these effects in those scenarios? This is also an interesting question. For example, like I talk about some of them, for example. Do I talk about some of them? No, I'm not sure. Doesn't matter.
Okay.
This. So some variations on the Schrödinger equation, what happens then, no? Things like this.
Mhm.
And then applications, it's quite hard. I mean, we just did this. Somehow, there are some potential applications in testing quantumness that, the details are still a bit unclear. But I think it's doable because there's a similar problem. I don't know. Maybe I'm going to go on a bit of a tangent here. But
That's
do you
fine.
know do you know Boris Trillo?
No.
Okay, so he's an amazing mathematician who solves lots of problems in quantum information that passed away quite recently, sadly.
Okay.
But one of his last papers that he put on QuantPH, on the archive on QuantPH, was studying a harmonic oscillator. What's the probability of having a positive position? And this paper really inspired us for this problem as well. So I have a harmonic oscillator. It's a particle oscillator, no? In a harmonic potential. Classically, it's very clear what it does. It's just, I don't know, a pendulum with a small angle or whatever. It's a very common approximation as well.
Mm-hmm.
And quantumly, it's also very interesting. And it's the basis of many things. But then you compare. What's the probability of, if I measure the position of a harmonic oscillator at some times, what's the probability of it being in the positive real axis? So to the right of its center of oscillator, let's say.
Mm-hmm.
And you can prepare quantum systems for which this probability is bigger than the classical system. This is crazy. And the group of Valerius Karani in Singapore has used this to devise tests of quantumness and new tests of entanglement, for example.
Mm-hmm.
So I'm thinking that similar things could be done with the rocket. Like the Aspelmayer group in Vienna, for example, is interested. He has these optical traps for atoms. And then maybe with this we can test if the atom is in a quantum state, something like that. It's still very in the air,
Mm-hmm.
but it can have It could have we don't know yet. It could have applications in detecting quantumness, which is a very important problem. Maybe entanglement. What happens if this was an interesting question? What happens if you have two projectiles simultaneously going one in this direction? I don't know. This is something I joke about, but can we violate the CHSH inequality faster than anyone else? There's lots of possibilities. It just, we don't know. But what it does not have applications on, at least not right now, is on actual transport of matter. This is one when you emailed me about this. I was like, well, I don't know if this is what you want. Like, really are not going to be a quantum rocket per se.
Right. No. I think that's clear, especially from especially from the results related to the actual rocket itself.
It has applications inside the field of quantum mechanics, but
from my perspective, I would be
this
fine.
is maybe a good thing. It doesn't have applications in war or anything.
Well, nothing yet. Anyway, we'll see where
they will surprise us. Yeah, I know.
Anyway, from my perspective, I'm happy with these questions. I don't know if there are any more things you would like to say, like any perhaps areas of research that you would like to see other people take similar fields or anything like that. If not, then I'm happy to conclude here.
Yeah, no, I'm happy with this.